Welcome to Numerical Methods. So in the last session, I started a new chapter, a new topic. So we were looking at American Monte Carlo, the valuation of Bermudan options within the Monte Carlo simulation. And maybe I start with a small recap of the last session. So the Bermudan option is essentially an option on an option. So you have you have several exercise states, where you have a right to choose from an underlying. So here are our exercise states given, and you have the right to add these states to exercise in some underlying financial product. So you will receive either a payment or a financial product with a given value at that time. You have this right once, so you can exercise in such an underlying at one time. But if you do not exercise, you see that you have the option to exercise at the next time. So if you do not exercise in TI, you have the right to exercise in the next time TI plus 1. So there is the choice between the underlying or the option at the next time step. So it's an option on option. Of course, you like to maximize the value of your decision. So the exercise strategy is to choose the maximum of the values that you observe, that is the value of the underlying and the value of the future Bermudan option. So the value of the Bermudan option is defined iteratively, going backward through every exercise state and maximizing each decision. We also noted that it is convenient to look at relative prices. So relative prices means that I divide all those values by the numeraire, by the respective numeraire, because then the relative value at an earlier point is just the expectation of the relative value at a later point. So we had here this nice formula that if I would like to calculate the value at an earlier point, I just need to take the expectation operator. And then you see that the evaluation of the Bermudan actually is an alternating interleaving of these two operations. So take the expectation of the value at the later time, which gives you the value at the current time. And then on this value, apply your exercise criteria, so maximize this. So you see, you get from the expectation here the value of the Bermudan that has exercise states starting in TI plus 1, but observed in TI. And then you plug this in to your exercise criteria to get then the Bermudan at this evaluation time with this additional exercise date. Okay, so this is more or less the definition of the value of the Bermudan by maximizing the value obtained upon exercise. And then we had a very nice algorithm to construct this value of the Bermudan. This was the backward algorithm. So it's essentially exactly this, that we go backward, and at every exercise state, we look at our exercise decision. So is the value of the underlying less or greater than the value of the future Bermudan so the expected value of continuation. But there was a subtle modification. If the underlying has a higher value, we exercise, so we get the value of the underlying. But if we do not exercise, we just take the random variable that contains on every path the values of the underlying that we get at the corresponding future exercise time. So the subtle modification that is quite important was that there is no expectation operator here. So we define this random variable u tilde I, by just updating every element according to the exercise decision and putting the value of the underlying there. So there was a small picture here. So on the left side, here you have the value of the underlying at each time, and then on the right side you update this random variable u tilde I by going backward and checking, do you take the underlying value or do you take the continuation value, the value that you had already in this vector? So in the end, you have a vector that contains all the values of the underlyings that you take at the optimal exercise time. And the nice result is that the expectation of this random variable, so the unconditional expectation of this random variable that we get in the end, so the u tilde 1, this is the value of the Bermudan. So we just need to do the unconditional expectation once on this random variable. The conditional expectation operator is still there, but important, it is only in the decision. So the conditional expectation operator is only here in the exercise criteria. So here again, you see our small modification. So in the backward algorithm that constructs this random variable, we take here the continuation value on every sample path. In the classical definition, you would take the value, the expectation operator on the value of the Bermudan to define the value of the Bermudan at the earlier time point. The exercise criteria in both definitions stays the same. And taking the expectation on the upper part will give us the value of the Bermudan. Why was this small modification important? So we had a very nice little picture. So this little picture here is, say, a Bermudan option with 2 exercise dates. So we have the right to exercise in time t2 into some underlying, which I call v2, or the value process is v2. And this is maybe an option on the stock observed in time t2 with a strike k2. So you can take that, or you can take at an earlier point in time an option v1, so observed in t1, which is maybe just a classical European option on the stock observed in t1. An option with strike k1. Strike may be different, so you see here the strikes are a little bit apart, a little bit shifted. Well, this value here has to be compared to the value of this seen in t1, so to the expectation. So I have to compare this to v2 observed in t1. So this guy is now the valuation. So take the numeraire in t1, multiply with the expectation of the vt2 divided by the numeraire in t2. And this is the conditional expectation. If my model is a Black-Scholes model, you could use the Black-Scholes formula for this. And here in this little picture, we could nicely illustrate why it is important to use our conditional expectation only at the decision, or only in rare cases, as seldom as possible. Because if your conditional expectation is given by a numerical method that just gives you an estimate, maybe a poor estimate, then if you just have this error in the decision criteria, so what would you do? So you would exercise when you cross this point, yeah, because this here is your conditional expectation. It's higher than the green line. So you believe that you get a larger value if you continue. And here, this is your conditional expectation. It's smaller than the green line, yeah, so you believe you get a higher value if you exercise. So this is the exercise point that you have when you take the orange line, the estimate for the conditional expectation. The correct value would be the blue line, so this guy here. And you see there you would exercise at this point here, because you see that the value that you get is actually higher up to this point. So if you take only the values, if you take if you take the estimate only in the decision, I assume that my Monte Carlo simulation can calculate the blue line here correctly by taking the unconditional expectation of the future underlying. Yeah, so taking the expectation of this guy here would give me today the right values. Yeah? So if I take it only in the decision, what we get is actually, we do not exercise, so we get the correct value. But then we exercise at the wrong point. So here we would say exercise, so take the green values. And this would be what we get if we use our poor estimate in the exercise criteria. So you see the error that we make is actually just this area here. This is the error that we make, and this error is quite small. Yeah, it's just coming from not having the right exercise time. If you would also use this poor estimate in the values that you aggregate, yeah, that you accumulate, you would actually take these values here up to the exercise point and then continue on the green line. Yeah? So you see that this error is much larger, yeah, because you also make, in addition, an error in the values that you accumulate in your Monte Carlo simulation. Yeah? So this is the difference if you have here these values also there. So that was maybe a small recapitulation. And we saw that everything boils down now to calculate the conditional expectation in a Monte Carlo simulation. And we also had two, methods to do this. Actually, the methods did not work. So the first one was resimulation. Okay, so if you need to calculate a conditional expectation, for example, at this point, yeah, you just start a new Monte Carlo simulation at that point and simulate new sample paths here, with, say, your initial value or whatever defines your condition. And if your Monte Carlo simulation arrives, say, at that point, you also start a new Monte Carlo simulation, creating a different distribution here, yeah, that is then used for the conditional expectation. Yeah, of course, this resimulation has the problem that we have a very high complexity, yeah, so the effort needed grows exponentially. Then another idea was creating perfect foresight. So this idea is that, yeah, I do a kind of resimulation. So if you need to calculate the conditional expectation here, you do a kind of resimulation with a single sample path, namely the sample path that continues from there. So if you take the sample path that continues from there, you just take here the value at the end as your conditional expectation at this time point. Yeah? So you just define the conditional expectation by the single values that we observe here at the end. Yeah? So just take this guy on every sample path. If you do this, then you immediately see the problem here. On the left side, you have a random variable that should be ft1 measurable. Yeah? Conditional expectation, conditional to your knowledge in time t1. This is ft1 measurable. But on the right side, you have a random variable that is maybe not ft1 measurable. So it's ft2 measurable. Yeah, that is true, but it is maybe not ft1 measurable. So you know something about the future. So you base your decision on knowledge about what you get in the future. So you could have a different decision, yeah, on a sample path that has the same past, but that has different futures. So for example, here, doing the correct decision would be to compare the expectation of getting either 4 or 1, which is 5 divided by 2, which is 2.5, to compare this with what you get if you exercise, with the 2. So you would not exercise, you would continue, because in expectation you get more. But with perfect foresight, you would compare each guy individually with the 2. So because you know you can distinguish whether you are on omega 1 or omega 2. Yeah, you have knowledge about the future. So it would mean that in omega 1, on sample path omega 1, you would continue and get the 4. On sample path omega 2, you would exercise and get the 2, which is a 6 divided by 2, yeah, which is a 3, which gives you a higher value. Yeah, you can extract more money out of this option because you have knowledge about the future. So this is perfect foresight. Perfect foresight or foresight bias will also appear in approximation methods, yeah, because sometimes the approximation method cannot remove knowledge from the future. So you do some kind of sampling, and inside there is maybe hidden knowledge about the future as some kind of noise. Yeah? So you can get a foresight bias. So that was more or less a recapitulation from the last session. And we now have a nice numerical experiment. So this is what I would like to start with, that I would like to recreate the figure that I have discussed. So this is this guy. I would like to recreate this with a program, and maybe also just try to evaluate the Bermudan option that we have here. So the Bermudan option with 2 exercise states. I like to do this by assuming a Black-Scholes model. And this has some advantage because in the Black-Scholes model, I can calculate this conditional expectation analytically. So if you go back to the figure, this blue line here, which is what I get if I continue expectation in T1, this is just the valuation of this payoff here in time T1. Conditional to where I am in T1, so conditional to where the stock is in T1. So this here is the Black-Scholes formula, but you have to be a little bit careful. It is the Black-Scholes formula with, what is the time parameter in this formula? The time parameter is the remaining time. It is T2 minus T1. Okay. And what is the initial value, the spot of the stock? This is not today's value of the stock, so not S in T0. It is S in T1. So the initial value is a random variable, yeah, because I can have different values of S of T1. So the good thing is that for this conditional expectation, I can use the Black-Scholes formula. So this is a rare case. So I have an analytic formula. So this is good. Yeah, so my conditional expectation is quite accurate. But note here, this is a Black-Scholes formula where the initial value, the spot value, is a random variable, because we already simulated up to time t1. So, and have different values of where we start, yeah, like in the picture with the simulation, and the time to maturity is t2 minus t1. So maybe we try this in the computer. Okay, to save a bit time, I have prepared a few steps already here, but this is all the stuff you know, because I create here my Monte-Carlo simulation of a Black-Scholes model. So this is just create a Monte-Carlo simulation of a Black-Scholes model. What are the parameters we use? Initial value for the stock. Yeah, so this is my, say, S of 0 is 100. The risk-free rate, my R is 5%. The volatility, so my sigma is 30%. Initial time is 0. So this would be maybe my T0, if you like, yeah, or in simulation times it is T0. The time horizon is 2 years, and the time step size is 1. So actually I simulate 2 steps, yeah, from 0 to 1 and from 1 to 2. Because I just need these 2 steps, my Euler scheme is exact, and I have an option that has exercise at these 2 times. Yeah? So I need to have the stock value in time t1, which is 1, and the stock value in time t2, which is 2. Monte Carlo simulation, 5,000 sample paths. Yeah, I just want to do a few plots in the end, so I do not need so many sample paths. Monte Carlo seed. My Bermudan option, so my financial product, should have 2 exercise times. So this is here T1. So T1 is 1. And in T1, I can exercise in a payment that is maximum of S of T1 minus K1 and 0. And K1 should be 120. So this is like in our figure here. So that would be the green line, and the K1 is here my 120. Then I can continue and I cannot exercise. So there is a second exercise time here. That is my T2. So this should be in 2. And the K2 is then a little bit larger. So this is the 140. So in time T2, I can exercise in this payoff with this K2 here. So it's a bit larger. So if you take the value of this payoff here at an earlier time, it will be this curved function here. This will be my Black-Scholes formula, and there will be some point where we intersect the other payoff, because the other payoff is dropping to 0, but the value of an option is higher than 0. So let's try and value a Bermudan option, and I would like to do it in the right way and in the wrong way. So the wrong way is I would use perfect foresight. So I need, of course, the random variables, the stock value in T2. So this is my S of T2. So I ask my model, okay, please give me the value of the stock at time T2. So this is my S of T2. And I would like to have the stock value in T1. So this is, please give me the value of the stock in time T1. So then I can calculate the payments of the underlyings. So the payments if I exercise. So this is the random variable. The value of the option 2, my V2 in time T2. So if I would exercise, so this is the S of T2 minus the strike, yeah, but which strike? It is the strike 2. And then from that, the maximum of this and 0, yeah, so floored by 0. So this is my V2 of T2. Yeah. So maximum of S of T2 minus K2 and 0. Alternatively, I can exercise in option 1. This is done in T1. So this is the stock in T1 minus the strike K1. So this would be my V1 observed in T1. So this is maximum of S of T1 minus K1. Okay, so these are the two underlyings of my Bernoulli option. Now I have to decide whether I exercise in T1 or whether I continue. So I have to have an estimate, yeah, or a good approximation, whatever, for the conditional expectation of this guy. So I do not yet have a numerical method to estimate the conditional expectation, but in the special case that I have a Black-Scholes model, yeah, so we have Black-Scholes model here created. In that case, I know this guy analytically. So this is now the random variable. It will be a random variable, the value of the option 2, but this value seen in T1. Okay, so this is Black-Scholes formula. Okay, so let's take Black-Scholes formula, analytic formula. There is Black-Scholes option value. Okay, so you have Black-Scholes formula with arguments, initial value of the stock, R, sigma, option maturity, and option strike. Yeah, so this guy gives you the value of the option. What is the initial value of the stock? Well, we have with our simulation arrived in time T1. So let's take this picture of the resimulation, which is always a good thing for the intuition. So this here is the time T1 at which I now would like to make my exercise decision. So the stock has already moved. Yeah. So I'm not here in 0, where I know it is the initial value of the stock. I'm here in time T1, and I can have different values for the stock where I start. So I use Black-Scholes model with these different initial values. And because these different initial values are random variable, actually I have Black-Scholes model, Black-Scholes formula applied component-wise. The result is also a random variable. And what is the time? The time to maturity for my Black-Scholes model is this interval. So it's from T2, from T1 to T2. So it's T2 minus T1. So I have to be a little bit careful. But the nice thing is, if you look here, there is a function implemented, Black-Scholes option value, that takes as arguments random variables. All these arguments here are now random variables. So which random variable should I use as the initial value of the stock? Yeah, so this is the stock in T1. Okay, the other parameters are not random variable, and I can also pass them as floating point numbers. So this is the risk-free rate, the volatility. What is the maturity? Yeah, the maturity is not maturity 2. Be careful here. It is maturity T2 minus maturity T1. So it's T2 minus T1. What is the strike? The strike is, it's the option in T2, is K2. Okay, so this Black-Scholes formula here operates on random variables. So you can maybe look it up. Yeah. So you see all the operations here for the D plus and D minus and the application of the cumulative normal distribution. All these guys are now defined in terms of random variables. So it's a Black-Scholes formula in terms of random variables. Yeah, now this is the conditional expectation I would like to have. So maybe I move all the values to numeraire relative values. So let's call it value relative. So this is just the value that we have calculated divided by the numeraire. So the value of the option 2 in T2, this has to be divided by n of T2. The value of the option 2 in T1, this has to be divided by the numeraire in T1. The value of the option 1, the underlying 1 in T1, this has to be divided in by also the numeraire in T1. Okay, so all the values are now numeraire relative. Yeah, actually this is here needed, yeah, because if I would like to do the perfect foresight, yeah, I would take this as my estimate for the conditional expectation. So the perfect foresight was that I take the value of the option that I observe in the end divided by the numeraire. Yeah, I always compare numeraire relative values. So I can calculate now my Bernoulli option value. So let's construct this random variable u. So this is my Bernoulli pathwise value. Yeah, what do? I have my exercise criteria. Do I exercise or do I continue? My exercise criteria is the value of the option in T2 observed in T1. So this is what I get if I continue. So actually, this is my conditional expectation estimator. So this is my Black-Scholes formula. And from this, I subtract now, what do I get if I exercise? The value of the option 1 in T1. So I compare here both values observed in T1. So the option if I continue, V2, and the option if I exercise. Then I have a nice function, this function choose. So this choose function gives me this value if this random variable is larger or equal 0, or that value if it is less or 0. So if it is larger, yeah, actually I would like to take this guy. If it is smaller, I would like to take that guy. So this is just the maximum function, yeah, based on this criteria. And now comes the modification from our backward algorithm. So I do not use the conditional expectation in the values, I just use it in the decision. Actually, here it would be not such a big problem because my conditional expectation does not have a big approximation error because I have this analytic formula. But if this would be an estimate, it would be important here that I just take the value of the option 2 that I get in T2 if I continue. And since these are numeraire relative values, I can do this. Yeah. Okay, so this is the Bernoulli value, random variable, and from that, yeah, the expectation. Actually, I would have to multiply with the numeraire. So let's do this. So this is the Bernoulli value now. This is the expectation of this guy. Okay. Well, the expectation of this guy multiplied with the numeraire at evaluation time, so at initial time. So this expectation is an unconditional expectation, so I just can get the floating point double value. Yeah, I already have the print line here, so maybe let's try and run this. And I get the Bermudan value is 9.5. Yeah. Do we believe this? Maybe you can try this at home and check, yeah, compared to the two different European options. Yeah. So what do we get if you just exercise always in T1, or what do you get if you just never exercise? Now let's try the approximation with perfect foresight. Yeah. So do not use the Black-Scholes formula, just use this quantity here as your exercise criteria. So this would be another random variable. So this is now Bermudan pathwise value, and this is with foresight. Okay, so you base your exercise decision now on the value of the option 2, but not as here observed in T1, observed in T2. So you already know what you get in the end. From this, you subtract the value of the option 1 in T1, and then you make here exactly the same choice. Yeah? So I just modify my exercise criteria. Yeah, so let's calculate the value of this guy. So this is Bermudan pathwise value foresight, multiply with the numeraire in evaluation time, take the expectation, and this I call then the Bermudan value with foresight. So just the different exercise criteria here. So just this part here is different. And I now have knowledge about the future in my exercise decision. A small typo here. Okay, I just realized that I made a small mistake here. Yeah, you see this guy is yellow. Yeah, maybe also nice little thing. He reminds me that I never used this random variable here. Of course, in my exercise decision, I should use here the value numerical relative of the option in T1. Yeah? So this is the correct way to value the Bermudan option. Yeah, compare the numerical relative value. Yeah, also here with the numerical relative value. So compare the numerical relative value of the option 2 observed in T1 with the numerical relative value of the option 1 in T1, and take the larger one. But if you do not exercise, you just take the continuation value. And then we have the same criteria here below. So compare the numerical relative value of the option 2, but now with foresight, so seen in T2, to the numerical relative value of the option 1 in T1. And this is your exercise decision, whether you should continue or you should exercise. So let's run this guy. Okay, and yeah, the figures are slightly different now. So you see the correct evaluation without foresight, the value of the option is 9.2. If you include this foresight that you have knowledge about the future, the value of the option is 11.9. Okay, so we valued the two options, and then my task here in this numerical experiment is that I should maybe create this plot. So plot the continuation value with different colors, yeah, depending on whether you exercise or not, and maybe also create two plots, one using the correct exercise criteria and one with perfect foresight. So you find this in our lecture repository, and maybe I don't write this live and we look at the final version. So this is here exactly the same program that we wrote now. So with the printings. And now there is some plotting. Okay, so let's first maybe stop here and plot the continuation value. So the value that we get if we do not exercise in T1 and if we continue as a function of the stock observed in T1. So this is this picture. Here on the horizontal axis, I plot the value of the stock observed in T1. And on the vertical axis, I would like to plot now the value that I get if I continue. Okay, so this is the value of the option 2 in T2. So how does this plot look like? So this is the continuation value. Yeah, maybe I only plot this guy, so I comment the two other plots, I comment them out. Okay, so this is this plot. Yeah. This is the value of the stock that we have in T1. And then think of the picture with the resimulation. The Monte-Carlo simulation continues, and it will have different values of the option in time T2. Yeah, so for any initial value, you will see different values in the future, so different values of the option in time T2. Of course, if the initial value of the stock in time T1 is smaller, chances that you go up again and get a high payoff are lower. Yeah? So that's why you see here some kind of increasing in the values by increasing in the underlying stock value in time T1. This is our continuation value. And now let's plot the conditional expectation operator. So our expected continuation value. So what is our expected continuation value? So this is the plot that plots now as the x-axis the value of the stock in time T1, and then the value of the option 2 in T1. So this is this guy here. So this is just our Black-Scholes formula divided by the numerator. Okay, so let's plot this. Yeah, and you see this here is our Black-Scholes formula. This is now an important picture for the understanding, for the understanding of the next steps that we will do. So the value that you have here is the conditional expectation. Well, conditional to what? Yeah, conditional to ft1. But what is actually determining ft1? So the ft1 so the condition is that the stock has a certain value. So if you think of this picture with the resimulation, that the value of the stock started here at this point. Yeah. So given that in T1, my stock has reached this value, this is the conditional expectation of getting the future payoff. So this is my Black-Scholes formula with the initial value being this S star. So here in this case, it is with spot value S star. Yeah, so recall this is exactly what we do in the code. I take Black-Scholes formula and the stock in T1 is the initial value. And now I plot this value as a function of the stock in T1. So this is what this blue line is. I will continue here in a minute because this is now a very important observation. But maybe let's continue and do the other plots. Okay, I have two other plots here, which I can show. So this one is now plotting how the Bermudan exercises together with the two other values. And this plot is plotting how the Bermudan would exercise if I would have this foresight bias. These values here, actually I plot them now in different colors. So this here is some kind of dark green. This here is some kind of green brown. Let's also have a look at these two plots. So this here, actually it's the last one. It's the Bermudan option when I use perfect foresight. Okay, so the green brown dot here, this is the value we get if we continue. Also, this here is the value that we get if we continue. So if we don't exercise, so this is here the continuation value. So this is the region where we do not exercise. And the red ones are the dots where we exercise in the underlying. And now you see what perfect foresight is doing. Whenever he sees that a dot is above the value that we get if we exercise, I don't exercise. But when a dot is below, we exercise. But actually, conditional expectation should have a consistent criteria for such a given initial value. So there should be no difference between these two regions here. So here I always have knowledge about the future that if I continue, I will be below the value that I get if I exercise. So there I exercise. Here I know I will get a higher value. I continue. So you see in this corridor now, this dot here gives me a higher value. This dot here gives me a smaller value. But actually, I should base my decision on the conditional expectation. So maybe I should just count the values in this corridor and then base my decision on this estimate of the conditional expectation. So this is what perfect foresight is doing. So these are the guys here with foresight. So this is this plot here. So I plot the Bermudan pathwise value with foresight. The Bermudan pathwise value with foresight was our exercise criteria here, where I have knowledge about what happens in the future. This is now the plot where I plot the exercise values using the correct admissible criteria. Okay, and you see that your exercise criteria is now based on this point here, where your conditional expectation, so what you get in expectation if you continue, crosses the value of the underlying. And you see that there's a sharp line here that now divides the points where you exercise. So on this side here, you exercise into V1, So you get V1 of T1, which means that you get here this green line, it's above. And here you continue. So you take V2 of T2. And now your exercise decision is based on something that is FT1 measurable, because it is based here on the stock, as of T1. Okay, so maybe you can study a little bit this program, yeah, and this may be quite helpful because now you see how all these quantities are calculated. So this figure here that we have created gives us maybe now a good intuition how I can construct a very nice conditional expectation estimator. Because first, what you see is my conditional expectation. I wrote it is the value that we get if we continue, conditional to f T1, conditional to the information I have in T1. And this here, a sigma field from my filtration, is a quite abstract object. So what does it mean? What is this? But here in this writing, you see that I can express the condition to conditional that some random variable has some value. So this is now an important next step. I can interpret the conditional expectation as a function that depends on some other random variables. It's a functional dependence. So based here maybe on the figure that we had for this resimulation, so this was our figure for the resimulation, we already got this intuition that we can express the conditional expectation as something that depends here on this value where we arrive in time T1. So the resimulation differs by, maybe just the initial conditions of how we initialize the model that creates the resimulations. So for example, just the initial value of the stock, if we have our Black-Scholes model, but could also be something more complicated. For example, a full interest rate curve is the initial value of an interest rate model. And also sometimes, depending on the financial product, the initial value can be more complex, because if you have an Asian option that has already accumulated some kind of average, this accumulated average is also an additional initial value for your conditional expectation. So conditional to what you have accumulated so far. So it can be path dependent. So must not be just the value that you observe in time T1. It could be a collection of value that you have observed up to time T1. But still, it is a function of some observations of some random variables. Let us maybe just assume that there is a random variable, and this random variable z here, this is now my condition, this random variable z, so I assume this is maybe some vector. So it could be a collection of multiple values. I have a nice example in a few minutes. Multiple values that describes here this random variable z. And let us now assume that this random variable z generates our sigma field ft1. So all the information that I need is contained in this random variable. Then clearly conditional expectation conditional ft1 is the same as conditional expectation conditional to z. However, this identity here could also hold in cases where z does not generate the sigma field ft1. Z is ft1 measurable, but maybe Z is generating some smaller set, a subset of ft1. Because this identity here could hold anyway, because I just need to look at what are the quantities on which the future payoff depends. So for example, in my Black-Scholes formula in the computer program, so that's the reason why it's always nice to have such an example, you see that the conditional expectation here was only depending on the initial value of the stock. So immediately you know that there is a single random variable, namely the initial value of the stock, your S of T1, that you could use, and you see that expectation conditional that S of T1 has a certain value is the conditional expectation. The reason is because it does not matter what S of some other earlier time point has. Yeah? So there is no path dependence. It just mattered where you end in time T1. It just mattered. It doesn't matter which path you took. Yeah? For other options, it could be different. So I make this now here as an assumption. So I just assume that I have such a random variable set. So if you have such a random variable set, what does this mean? Conditional expectation is a random variable. Yeah? Also, expectation is a random variable that is constant. Yeah? Conditional expectation is a random variable that has maybe some subsets where it is constant, the condition sets, the sets that generate the sigma field, but it is a random variable. If I now plug in to the conditional expectation, conditional ft1, if I plug in a sample path omega, so I express the conditional expectation ft1, I express it as conditional expectation conditional to z. If I plug in a sample path omega here, it means that I'm looking at the conditional expectation under the condition that z is equal to z of omega. So all the omegas where z has a certain value. If you go back to our picture with the resimulation, this is exactly what I'm doing here. Yeah. So if z is my stock value, these sample paths here that I see here in the future, these are all the sample paths for which S has a specific value in time T1. So I condition on these sample paths, I condition on this set. So maybe you could call this guy here little z, yeah? So little z is now capital Z of omega. Then you see that your conditional expectation is a function of this little z. So your sample path omega is now here this little set, and you can express the conditional expectation as a function of this underlying value. This is exactly what we have here in this picture. Yeah? So this blue line here is my f of little z, where now the little z is the observation of the stock at time t1. So this is my Black-Scholes formula. Yeah, with the corresponding initial value z r sigma, yeah, t and k. So this thing here describes the condition. Okay, so I can describe my conditional expectation as a certain function, yeah, and then you just need to check, is your underlying value larger or equal that function, and this is your exercise criteria. Actually, here I have a small example where you also see that your exercise region, yeah, can be an interval. So there could be multiple points where where the two lines cross. You just check on the random variables, is f of z larger than the value of the underlying. Okay, so this is just the summary, yeah, what I just that. So we assume that I have a random variable. So the best case is that the random variable generates the sigma field, but it could also be that I just have a random variable that is smaller than our sigma field. Yeah. So it's measurable with respect to a smaller sigma field, because the functional dependence in the quantities for which we would like to calculate the conditional expectation, yeah, it is such that it depends just on a subset of these quantities. Let's have a nice example for what could be a very general random variable z. So assume our model primitives, so the things that we observe on our financial market, the x, yeah, they are only required for the financial product at discrete times, x of tk, say for example for the Asian option. And these guys are generated here by this Euler scheme. This is my model. So I have a time discrete model. Yeah, then if you arrive at some time t1, which is in your simulation time discretization a little tm, so I have made m steps in my model to arrive at this time t1, what is now describing the sigma field ft1, so on which you condition? Well, this is completely described by all the Brownian increments. Because if you know all the Brownian increments from T0 to Tm, so these are m increments, then you know exactly the sample path that you have walked up to time T1. Yeah? So you know you draw some Brownian increments, and either you get here, or you get here. So you have different Monte-Carlo sample paths. Okay, and all those Brownian increments encode what has happened in the past. So they encode the information that is available in FT1. So I can express now my conditional expectation as conditional to this random variable, so conditional to this function. There's another example for interest rate models. And now I would like to describe methods that allow me to derive this functional dependence. So I'm now one step further, moved from the abstract ft1 conditional to the z conditional. So I would like to describe the conditional expectation as a function of this set. And going back to our little computer implementation, there was already an idea. So here in my little experiment, I had this picture. And here I have drawn this little corridor, and I have a little bit looked at the different points that lie in this corridor. So maybe I can estimate the conditional expectation by defining some kind of corridor, some kind of interval around the value on which I would like to condition. So maybe I would like to condition here on this value. So this is now my little z. And I just count the points that lie inside this guy here. I just count these points, and I just average these points. This is maybe a very nice method to estimate the conditional expectation, which is the expectation of these values here, conditional to that the stock has a certain value, so as a functional dependence. And this technique is called binning. So in our Monte Carlo simulation, this conditional expectation is given by averaging over all sample paths for which Z attains the same value. Yeah? Capital Z equal this little z. And if you go back to our example with the perfect foresight, so this was the figure 39, this would already fix the foresight here in this example. Because if you condition on all the sample paths for which the stock has the same value, then this would mean take all the sample paths for which the stock has the value 2. So take S of T1 inverse of 2. And that means average over all the sample paths that have the same value. So average over these two sample paths. So in this example, I would average over the whole omega, because I just had in this example the two sample paths, and this would remove our foresight error, our perfect foresight. However, there is a problem. In a general situation, it is such that there are no two sample paths for which Z attains the same value. So your simulation usually looks like that. So you have sample paths and they are all different in time t1. Yeah. So there's only one sample path going through this value. And now you can improve this by introducing what I call binning, the binning method. So instead of just taking a single value, I take maybe some kind of corridor, some kind of epsilon neighborhood of a given value. So instead of saying that Z should be equal to Z of omega, I say that Z should be in the neighborhood of Z of omega. So I approximate this here, the conditional expectation, conditional to Z of omega, Z having a specific value. I approximate this with the value hi, where hi is just the conditional expectation over a larger set. Wait, this here is actually slight modification. Yeah, okay, so maybe let's go back. Okay, but maybe I can add another slide modification to, instead of choosing an epsilon neighborhood for every given value, I could also start with, say, some partitioning from the beginning into different bins, estimate the expectation in every bin, which is the conditional expectation that I am in a certain bin, and then just check if my functional value lies in this bin, so in which bin I am. So instead of using here this epsilon neighborhood as my condition, I could also start from the beginning with the partitioning into disjoint sets UI. So I use now disjoint sets UI instead of using U epsilon of Z of omega. And I just check if my Z of omega is in the set UI. So these are disjoint ones. So there is one I for which Z of omega is in UI. And I take the conditional expectation for Z being in UI, I take this as the approximation now for the conditional expectation, conditional to Z of omega. Okay, so this looks like that. So if your value just depends on what is the value of the stock observed in T1, it would look like this. So you predefine a set of bins here, so different bins, and then you just decide, yeah, is your sample path going to this bin? Then the conditional expectation is actually approximated by all the sample paths that passed through this bin. This may still have some foresight bias, yeah, because you use few passes. Yeah, so the Monte-Carlo error will show maybe some bias, and your option could react on this. But it's surely better than using the single path perfect foresight. So in the script, you find now the formulation for our example with the Bermudan option having two exercises, yeah, formulated with this binning. So I describe the continuation value as a function of the underlying. This is what we have done in our program. This is what we also have done in the picture. And if you do this, you get this scatter plot here. So this is actually also what we programmed. So this is the stock at time T1, and this is what you get if you continue. This is just scatter plot. And now you estimate your conditional expectation with some binning. Yeah. So binning gives you now a piecewise constant approximation of this conditional expectation. So what you see here on the right is actually just the distribution of the points that you have here in this bin. Yeah, there are of course many values lying around here in zero, because sometimes the option pays you zero. So this is already a practical approximation method, numerical approximation method for the conditional expectation. Yeah, construct a reasonable set of these bins and average over the sample path that you have generated. So you do not need to generate new sample paths. The sample paths that pass through the given bin. But if you look at this picture, maybe there is an even better way of doing this. Because what we are doing here is we approximate this function here, conditional expectation as a functional dependence. We approximate this function by a piecewise constant function. The function that is constant on the specific bins. But you see there is some kind of cloud of dots here, and the function that is running through this clouds of dots. Maybe there's a better way to find the smooth function going through this cloud of dots. And this will be the next method. We can describe the conditional expectation as a regression, as a least square regression, minimizing the distance to the dots in this cloud in a certain way. And to understand this, the first step is that I can rewrite the binning method as a least square regression. So this will be then the motivation for the regression method, the least squared Monte-Carlo. Yeah, very important. Actually, this is what they all use, and this will be done then in the next session. Okay, that was it for today.